Okay, so we didn't meet last week, only because it was 4th of July and it was such a weird time right before the holiday. So I extended the Chapter 9 homeworks, which I'm sure everybody knows, to this weekend, and then you also have the first few sections of Chapter 3 due this weekend as well. I'm hoping you guys have a lot of questions. I really don't have anything planned for tonight. I was hoping we can just go through some Chapter 9 stuff if you have questions from the Chapter 9 stuff, and then even maybe some Chapter 10 stuff if you have questions from that as well. So let's just jump right into it. Anybody have any homework questions?
Uh, yeah, I have one.
What you got, Ian?
I was gonna ask, can you do the chapter like 9.4, 9.5?
9.4, 9.5. You said number 5?
Yeah,
All right. All right, cool. Yeah, so let's look at this one. I'll just read through it here. If a body of mass m falling from rest under the action of gravity encounters an air resistance proportional to the square velocity, then the body's velocity t seconds to the fall satisfies the following equation, where k is a constant that depends on the body's aerodynamic properties. Okay, great. So they give us this differential equation here. First thing they want us to do is they want us to draw a phase line for the equation. So let's kind of talk about that. Let me copy down the differential equation. M dv dt is mg minus kv squared. So the first thing that you have to do for this is you have to have the derivative by itself. So let's just divide that constant of m over. Okay, cool. So just dividing that m from each of the terms. All right. This is an autonomous differential equation. It's called autonomous because there are no t's on the right-hand side. We only have the variable v, which is good. That's what we want. So the first thing that we do for these phase lines is that we have to set this equal to 0. So we're just going to take that right-hand side and we're going to set that equal to 0 and try to figure out where is the velocity 0. Those are going to be the minimums and the maximums of the velocity. So solving this for the v squared, we're going to subtract the g over. Divide by negative k over m. The negatives cancel, and then it's going to be the reciprocal, so m over k. And then we should also take the square root. There's no point in taking the negative square root for this because we're talking about the velocity of an object falling. So it's not going to have a negative velocity. Or, well, I guess it depends on the reference frame, but we're just assuming, right, that a positive velocity is falling straight down. So we're only going to take the positive version. So this is going to be my turning point, not the turning point, sorry, the critical points, the square root gm over k. The other thing that we should do, and maybe you can get away with not doing it for this question, just because you can kind of look at the A, B, C, and D answers that they give you, but we should also take the second derivative of velocity and try to figure out what that is. So if we look back up here at the original derivative, and then I take the second derivative, we're going to do an implicit differentiation. The g out in front is just a constant. So the derivative of a constant is just 0. That disappears. But then we have this term. The derivative of this with respect to t is going to be the implicit differentiation. So the first thing we're going to do is we're going to do the derivative with respect to v, which is bringing the 2 down. And then we're going to multiply that by the derivative of v. So it's going to end up being negative 2 k over m v, and then there's going to be a dv dt that we throw at the end. But we know what dv dt is. That we just get from the original equation. So this dv dt we're going to replace with that g minus k over m v squared. the thing that we had solved for before with the derivative. Okay, then we set this equal to 0 and solve for that. We still get this parentheses here, but this parentheses gives us the same solution that we had before, that square root mg over k. This thing out front, the only way that this can be 0 is if v is equal to 0. But it doesn't make sense for a falling object to ever have a velocity of 0, so we can pretty much just ignore that one. Okay, all of that is to say that our phase line is only going to have the one critical point. It's only going to have that critical point at that square root mg over k, where remember the phase line that we're talking about is the v axis, or the velocity axis. This splits up our axis here into two different regions. We have everything to the left of the square root mg over k, and then everything to the right of it. So we're just going to think about something that is less than this and see what happens to our velocity, or the derivative of the velocity. So if I go back up to the original equation here, this one that we had solved for, and I try to plug in something that is less than the square root this thing here, the square root mg over k, just kind of think about what that does. If it is less than this, then when I plug this in, the square root and the square cancel out. But then I have this k over m, which is going to cancel out with this m over k. And then just remember that this is supposed to be a little bit smaller. So if this is a little bit smaller, it's going to make this to be a little bit smaller as well. Which means that the g subtracted by something that's kind of like g is going to end up being positive. So in other words, when we're on this side of the square root mg over k, the derivative of v ended up being positive. On the other side, the derivative of v would end up being negative for the same kind of argument. We also need to know what the second derivative does. You know what? I did that without really thinking about it too much. I'm pretty sure I'm right, but just to double check, I'm going to do it a little bit better. So this is a little bit smaller. Plug it in. Yeah, I kind of like that. Okay, so now we need to look at the second derivative, which is this thing down here. With this thing down here, if I plug in something to the left of this square root mg over k, I'm going to end up getting a positive value here, but then a negative value out here because of the negative sign out in front. So here, the second derivative of v ends up being negative. If I plug something a little bit bigger, I get something negative here and negative there, which means here the second derivative ends up being positive. All right, I'm pretty sure that's right. Just to double check, that is, which one is that? This one, I think. I think it's A. I like A. Yeah, let's go with A. Cool. So I know that some of that stuff is kind of out there, especially because there's not numbers involved with that, trying to figure out if things are positive or negative. If it helps, just replace numbers with the m, the g, and the k. Just plug in whatever you want to plug in for those constants, and then see what happens when you pick something to the left of this square root thing and then to the right of it. All right, there's still some more questions here. So part 2, sketch a typical velocity curve. So that is based on our phase line here. If we do look at the axis in this way, with 0 is here, square root mg over k can be up there somewhere. This, remember, is what we call an equilibrium value, because it's one of the critical points of the phase line. When I am above that value, we're looking on the right-hand side of it, my derivative of v is negative, the second derivative of v is positive. So when you have a negative derivative, that means you are decreasing. When you have a positive second derivative, that means you're concave up. So everything above this line here is going to be concave up and decreasing, which means it comes in and kind of does something like this, right? Everything below that line is first derivative positive, so increasing. second derivative negative, which means concave down. Increasing and concave down does something like this. So then you just want to pick whichever of these graphs kind of makes the most sense. And it looks like C is really our only option here. So if you look above the square root mg over k, concave up and decreasing, below square root mg over k, increasing but concave down. Oh, that's incorrect. Oh, I didn't think about the word problem part of it. So because it is starting from rest, that means we have a set of initial conditions. That means it has to start at 0, which means it has to be b instead. It can't be above the square root. The reason it can't be above the square root is because that is beyond what we call terminal velocity. And that's just not what our situation is doing. Our situation is falling from rest. So it has to only start at 0. It can't possibly start bigger than 0. So that was my mistake, just not listening to the question. Or not really reading the question. And then the last one here, we're plugging numbers in. For a 160-pound skydiver, where mg is 160, and with time in seconds and distance in feet, a typical value of k is 0.005. What is the diver's terminal velocity? So that terminal velocity is that equilibrium value, because that's what we expect the velocity to eventually be. So what was it? Square root mg over k. So we just plug that in. It's going to be the square root where mg together is 160. K, I think it said, was 0.005. Yeah. So we just take that into a calculator. I got one here. If I typed it in the right way. And then they want the nearest tenth. I got 178.9. Yay! Okay, so just to kind of go back and talk about this question a little bit. I doubt you'll see something like this on the final exam that doesn't have like numbers plugged in for you already. Although the concepts are all there, and this is more how like a real life situation would be kind of assessed and derived. So we're given this differential equation based on an object falling with air resistance. With this system, we'd want to come up with the phase lines where the different possibilities of our solutions. Because of the initial conditions, the only phase line that would make sense when you graphed it would be this one down here, because you have to have the velocity starting at 0. After that, we're actually plugging in conditions. Now that we have the equilibrium value, which would be the terminal velocity, plugging in some numbers into it gives us the terminal velocity. I don't know how much 178.9 feet per second is in miles per hour, but I'm going to look it up because I'm kind of curious. 178.9 feet per second to miles per hour. 121 miles per hour is how fast that skydiver's falling. Okay, cool. So does that help? Does that make sense for that question? I know it was kind of a hard one.
Yeah, that does help. Thank you for that.
Okay, you're welcome. I saw Lauren had one. Let's look at this one. 9.3, number 2. There's only 2 questions. I know you're only asking for part D, but to get to part D, I would just feel more comfortable doing the whole thing. And these are pretty hard anyway, so I think it'll be nice just to kind of go through these things all together. So these numbers might be a little bit different than when you guys did it. A tank initially contains 100 gallons of brine in which 50 pounds of salt are dissolved. A brine containing 4 pounds per gallon of salt runs into the tank at the rate of 5 gallons per minute. The mixture is kept uniform by stirring and flows out of the tank at the rate of 4 gallons per minute. Let Y represent the amount of salt at time t. Complete parts A through E. Okay. So the first thing that you need to do with these questions, this is what we call a compartment question, or you can think of it like a mixture problem, is to come up with the differential equation. So it goes ahead and tells you what to set Y to be. Y is going to be the pounds of salt. If Y is the pounds of salt, Then we have the derivative of y. This is going to be the change in the pounds per salt per unit of time, where unit of time is in minutes for this question. The change in the pounds of salt is going to be the amount of pounds per minute that is coming into the system minus the pounds per minute that is coming out of the system. So the pounds per minute that are coming into the system is coming from this sentence right here. A brine containing 4 pounds per gallon of salt is coming in at a rate of 5 gallons per minute. If we need pounds per minute, we're just going to multiply these two numbers together. That way the gallons cancels out. So 4 times 5, we have 20. And if you really want to, you could put units here. 20 pounds per minute of salt coming in. That's going to be minus the pounds of salt that are leaving the system. So the pounds of salt that are leaving the system is a little bit more complicated. We know the rate at which the liquid is leaving the system, but we don't necessarily know the concentration of the liquid at any particular time. But we can set it up using these variables. So what we do know is that the system is exiting out 4 gallons per minute of liquid from the tank. That tank has a concentration of taking the amount of pounds of salt at any given time, which is y, divided by the total volume of the system at any given time. That volume is almost always something that we can figure out based on how many gallons is entering the system and how many gallons is leaving the system. So I'm going to leave the y alone, but then this volume at the bottom, initially, we have 100 gallons of substance, and then we have 4 pounds that is entering, we have 5 gallons per minute entering the system, 4 gallons per minute leaving the system. Overall, that is a change of 1 gallon per minute. So I'm just going to take that 100 of the initial amount plus t. Okay, this is now my differential equation. This is a linear differential equation, which means we have to write it in that standard form. So this derivative, I'll write it as dy dt. I'm just going to leave on the left-hand side. But the term that has the y in it, I'm going to add over and rearrange it a little bit. So I'm going to write this as 4 over 100 plus t. All of that times the y, and that's going to be equal to the 20 on the other side. This means that I have my p and I have my q. The p is the coefficient on the y, that's the 4 over 100 plus t. Q is just going to be the value on the right-hand side, so just 20 in this case. We need to find our integrating factor. The integrating factor we get by taking e and raising that to the integral of p. P is this 4 over 100 plus t, so I need to take the antiderivative of that. And you can do some u substitution here and kind of fiddle with it. I'm just going to skip ahead. We pull the 4 out, then the antiderivative would be the natural log of 100 plus t, and we'd bring the 4 back in as an exponent. Then the e and the natural log would cancel out. We're going to end up with 100 plus t all to the 4th power as the integrating factor. So then if I take that integrating factor and multiply that on both sides of the original differential equation, on the left-hand side, all we're going to get is the integrating factor times y, and then the derivative of that product. On the right-hand side, we're going to have the q, which was already over there, times the integrating factor. Next thing to do would be to integrate both sides. When I integrate the left-hand side, it just cancels out with that derivative. Integrating the right-hand side, again, you could do a u substitution to get this, but maybe you can just kind of eyeball it. That 4 would raise up to 5, and then we would divide by that 5. Don't forget to add your plus c for that antiderivative. All right, last step to get the y by itself would be dividing by this integrating factor. When you divide it over here, you're just going to end up with a single 100 plus t multiplied on the 4. But the constant, on the other hand, is going to end up having that 100 plus t. I'll write it to the negative fourth. You could have put it in the denominator if you really wanted to. All right, we're not done. So the last little bit of this is that you can solve for the constant. And to solve for that constant, you're going to be using the set of initial conditions. Initially, at time 0, there were 50 pounds of salt in the system. So we're just going to plug that in. My y will be 50. And I'm just going to replace all of my t's with zeros. So this is going to be 400 plus c. This is going to be 100 to the negative 4, whatever that is, some really tiny number. If I subtract the 400 over and then divide by this 100 to the negative 4, that's going to give me my constant c. So this, maybe it's not too bad. Let me type it in the calculator and see what it is exactly. 100 to the negative 4. Oh, no, it's awful. It's some really, really, really tiny number. I'll just leave it like this. That means that my answer to this question, at least for part A, y is going to be 4 times 100 plus t, and you could distribute the 4 if you really wanted to, minus c, which was 350 over 100 to the negative 4, times 100 plus t to the negative 4. And that answer looks awful, and it kind of is. But let's type it in to see if we got at least part A right. Oh no. Oh, sorry. Thanks, Lauren. This is probably like the final answer, and they wanted it broken down into steps. I see. So I did all this work, but part A was only asking for the 20 that was out in front, the rate at which the salt is entering the tank. Okay, cool. B, what is the volume of brine in the tank at time t? So that's that volume formula that we found. That's the 100 plus t. Again, we got that because initially there were 100 gallons of liquid, of brine, and we have 5 coming in and 4 going out. So overall, a difference of 1 per minute. So that's why we have a 1T. At what rate pounds per minute does salt leave the tank? So this is going to be the last term here. This is going to be that negative 4 times y over 100 plus t. Just double check to make sure that's what they want. Yeah, I think so. Ugh, I guess they don't want it written like that, though. Oh, they don't want the negative out in front. There we go. So just the 4, which is the rate at which the liquid is leaving per minute, times the concentration, the y divided by the volume, 100 plus t. All right, now to the part we really care about, D. Write down and solve the initial value problem. So here where it just says to write down the initial value problem, all they want you to write down there is this part of the equation here. This. Oh, E, not D. Okay, cool. So this, we're just combining the stuff together, the 20 minus 4 over y, 100 plus t. I'm assuming that's what they want there. Great. E, what is the solution to the initial value problem? Great. That was all of this work that we just did here. Final answer is going to be this part. This is where we want the 4, 100 plus t, minus the 350 over 100 to the negative 4, times 100 plus t to the negative 4. Great. And again, we got that by taking the initial value problem that we'd set up and then solving that using that linear system, or the linear steps that we talked about in section 2. So it's finding the integrating factor, multiplying it over, and then integrating both sides. Oh, there's another part to it. Find the concentration of salt in the tank 29 minutes after the process starts. That would just be plugging 29 into this. Let's see, 4 times 100 plus 29. That minus 350 over 100 to the negative 4 times 100 plus 29 to the negative 4. All right, I think I typed that all in right. After 29 minutes, there's 389.6 pounds of salt. Ah, crap. Man, I got so excited. Oh, I see. They're asking for the concentration. They're not asking for the actual pounds per salt. They want to know the pounds per gallon. This is the pounds that we just found, but the gallon is now changed. There was 100 gallons. Now there's 129, because remember, every minute another gallon is added. So I'm just going to take that answer that I thought I had there and then divide that by 129 to get 3.0. Great. Again, that's me not reading the question all the way through and just trying to answer. Don't ever do that. Read your questions all the way through. Don't be like me. Okay, great. So that was that one. Is there any other questions about this one? I would say this is probably the hardest stuff that you had to do there from chapter 9. Any other questions about any other homework questions, chapter 9 or chapter 10? Anybody else? Chapter 9, chapter 10 stuff? I don't think chapter 10 is too bad once you get into it, but it's probably time consuming. I think there's quite a few questions in the chapter 10 homeworks, at least in the first few sections, so just make sure you set aside enough time to be able to finish it. I've seen that most of you have already done the chapter 9 stuff. A couple of you still have a section or two to do. So if you haven't done the chapter 9 stuff, you got to get that done as soon as possible, because the first 3 sections of chapter 10 are due this weekend as well. Did I post the chapter 10 videos? Yeah, this morning or this afternoon, I posted the chapter 10 videos, so they should be up now as well. I did also want to say that I already have most videos. Not seeing them now. I'll go look here in a second. I'd already made a lot of the videos for chapter 10 last semester when all of this started. So you may start noticing that the format of some of the stuff changes just because I'm going to be using the videos that I had made from last semester. Let me refresh and see if they're still there. 10.1, 2, 3. Yeah, they look like they're there to me, Richard. Oh, I did move them to the top. And that was very selfish, just because I was tired of scrolling all the way down through all those other videos to get to the chapter 10 stuff. So I moved the chapter 10 videos to the top of the Moodle page. So maybe that's why you're not seeing them. If they're still not showing up, though, let me know, because then I'm going to worry. You got them. Okay, cool. All right, last call. Anybody else have any other homework questions or any other life questions?